Okay, g'day all and welcome to another video. So today I thought we'd do something a little fun, well, kind of fun. Anyway, I joined Stack Overflow the other day and I was reading through some interesting questions, and one of them was this one person who posted some code in C++ to deal with the Collatz conjecture, or the 3x plus 1 conjecture. So what I thought we might do is have a bit of a crack at coding some really quick versions of this little algorithm that this guy posted on Stack Overflow, and hopefully with a bit of luck, we can demonstrate some of the ideas that go into making really high performance code in assembly language. So the Collatz conjecture is also called the 3x plus 1 problem. And this is the way that it works. You start with any whole number greater than 1. And if the number is odd, you multiply it by 3 and add 1. But if the number was even, then you divide it by 2. And you just repeat that over and over and over again until you get to the number 1. Now, so just as an example, if you started with the number, say 5, 5 is an odd number, so you would multiply it by 3 and add 1 to get 16. And then 16 is an even number, so you would divide it by 2 to get to 8. You would divide it by 2 again. Since 8 is even, you'd get to 4. Then you divide it by 2 again to 2, and you divide it by 2 again to 1. Yeah, another example, maybe you start on 3, for example. Yeah, if you start on 3, then that's an odd number, so you multiply it by 3 and add 1, you get to 10. Then you would divide it by 2, since 10 is even, and you would get to 5, and we know where 5 ends up. The conjecture is any number that you start with will eventually reach 1. Yeah, so there's a couple of options. There could be numbers that just explode to infinity and never come back down and reach 1. And the other possibility is there might be loops. So when you reach 1, 1 is an odd number, so you actually start going 1, 4, 2, 1, 4, 2, 1, 4, 2, 1, over and over again if you repeat the Collatz process. So the conjecture would be proved false if you could find another loop like that 421, 421. Yeah, but as of yet, nobody has managed to prove it either way. Mathematicians don't know, and neither do computer scientists. So the code that this guy actually wrote was to count the sequence. So how many iterations it takes before you reach 1. So a number like, I don't know, say 8, reaches 1 fairly quickly, since you just divide it by 2 to get to 4, then you divide it by 2 to get to 2, and you divide it by 2 to get to 1, so that takes 3. A number like 5 takes about 4 iterations, since we go 5 up to 16, then to 8, then to 4, then to 2, then to 1. Yeah, but what you'll find is the higher that you go, you start coming across numbers that take a strangely long time, you know, a strange little journey through very large numbers or numbers of great magnitude before they eventually seem to wind down and come to 1. It's also called the hailstone conjecture. Yeah, because these numbers, they get really, really great. They get huge, enormous numbers, but eventually they fall down like hailstones and reach 1. Okay, so here we are in a little driver program in C++. A couple of things about this little program here. We've got this cycle counter just here. So I made this little library. It's just I guess a wrapper for the RDTSC instruction so that we can count cycles. But here's the function just here. So I want to mention that in the original poster's code, he actually kind of got it a little bit wrong. And yeah, I'll stick to his version though. So in his version, he actually counts, if you start on 1, he counts that as a 1. But really that takes 0 steps to get to 1. So you might return 0 there. Yeah, but other than that, it's pretty good. The other thing to be careful of is don't put 0 into this function. At the moment, if it's 0, it just goes into an infinite loop. Anyway, that's the code just there that we're trying to optimize. So maybe if you want to have a bit of a go, just jump onto Visual Studio, type this out, and yeah, have a bit of a think about how you would optimize this program using assembly language. So it's a little bit tricky because this is not a good algorithm to use SIMD. Yeah, it's not a good algorithm to vectorize, so you have to think about other ways to do it. Anyway, so down here in main, I've just got rep count. So we're going to repeat the test 10 times. Then max n is 20,000. So we're counting up from 1 all the way to 20,000, and we're figuring out the Collatz numbers for all of them. And then, yeah, I'm just using the little cycle counter to record how long that takes. And after we've finished running OP's Collatz CPP, we've got this ASM version down here, which is what we're going to write. Okay, so if I just save that for a second. Okay, so if you had a bit of a think at how to do this, let's have a go on, let's have a bit of a walkthrough at one possible method for doing it. I hope this is helpful for people. I mean, I don't really know. Okay, so I've already included the build customization for Meshroom. What am I doing here? We'll call this, I won't call it Collatz, I'll just call it asm.asm. Okay, so we'll go code. And the first thing that we've got to do is state that we're going to have a procedure, and it's going to be called Collatz asm proc ret Collatz asm and p emd. Okay, so we'll just run this and see that it actually works. It actually doesn't. Oh, sorry, I've got a mistake. Collatz asm. Oh, we didn't include a. I should put it up here. Okay, extern C, it's an int. It's called Collatz asm, and it takes an unsigned int. I'll call it I, though you don't have to supply a name. Sorry, I forgot to put the declaration in. We will have to put that in. Otherwise, it's not going to know what's going on. We'll hit run and see what happens. Sorry, I'm trying. Sometimes I've got to lean over to look around the camera. Okay, so the average of CPP, what? -1. Why is that -1? Oh, sorry, we're not performing it 10 times. We've got to do at least 16. I'll go 100 times. We'll run it again. Okay, there we go. So this is the output of the program. So his original code has an average clock cycle count of that number just there, 85 billion trillion. The total that he came up with was 18 billion trillion. And the ASM at the moment is much, much faster, but the total is a completely random number. Yeah, so what we're going to try and do is make it so that our totals are the same. First of all, we've got to compute the same value, and then we'll worry about the performance ratio. Alrighty, let's jump over to here. I think the first thing we should do is say mov eax1, and then comp ecx and 1, and je to finished. Okay, so if the value that we're passed is 1, then we really don't want to do anything, so we can just jump straight down to finished. Something like that. Otherwise, we want to start a loop. So I always call my loops loop head when there's only sort of one of them. And at the end of this loop, we're going to want to check ECX. So we'll go comp ECX and 1. Oops. And we'll go jump not equal to loop head. Really, we should be checking for 0 as well, but like I said, the original code doesn't do that, so we might as well not as well. Okay, so to test if ECX, so ECX is going to be our current value in the way that I'm writing it here. To test if that's an even or an odd number, what we really want to do is just check if the lowest bit is set to 1, and you can do that with ECX or and ECX and 1, and then could do like JZ to even, or J and Z to odd. Yeah, but I guess the trouble with the AND instruction is it's actually going to change the value in ECX, and we don't particularly want it to, so we want something very similar to AND, but not quite the same. Okay, so test. The test instruction will set the flags exactly the same as AND, except it won't actually change the value of ECX. Okay, so if we go J and Z to odd. Okay, so if that was 0, then we'll fall down to here, and we can go shift right ECX and 1. So this step just here is divide the even number by 2. And then I might say something like jump loop tail. Yeah, something like that. We might also inc EAX. add 1 to the iterations. Okay, so if the number is even, it'll fall down to here. We'll shift ECX to the right 1, and we'll increment our little iteration counter. Otherwise, let me just see if I can look over the camera. No. Otherwise, we can fall down to odd, and we can say imul ECX by 3 and inc ECX. Okay, so this is ECX was odd, so multiply it by 3 and add 1. Okay, so by the time we've done that, we can probably inc AX again. This is add 1 to the iteration counter. And we can come down here to loop tail, which is where the whole loop finishes. Actually, I might just, since if it's odd or if it's even, we can do this add just here at the end. Yeah, just so that we don't have to repeat it. Okay, so that should just about be it. Really, if I just hit a bit of a save, we've got ourselves an assembly version of the original code. We'll hit run and see if we get the same answer as the, yeah, there you go. So total and total. But what you'll notice is, look at this. Okay, so the speed or the performance ratio of our code is 0.94, which means that we're slightly slower than the original code. I've got this in, this is a Microsoft compiler, and I've got this in release mode, so all of the optimizations are turned on. And I tell you, it's not easy to beat an optimizing compiler. These things are good at assembly language. So we're not there yet. We're taking slightly longer to perform this little operation. So if we come over here to ASM, we see that we've got some more work to do. What can we do? You know, optimally, we've got, so at the moment, if we look at this code, we can see that there's a whole bunch of labels and jumps in the code. So we've got loop head, then we've got a jump down here to odd and a jump to, loop tail. Really, in performance code, as much as you possibly can, you want to get rid of jumps. So every time the CPU mispredicts or tries to figure out which path it's going to take, and it gets it wrong, it's actually got to flush itself. So jumps can be very, very costly. We really want to get rid of those jumps. There's instructions called CMOV, or the conditional moves. What we could do to get rid of some of these jumps is compute both 3x plus 1 and x divided by 2, and then we could shift into ECX, whichever one it happens to be. So let's have a bit of a go at doing that. What I might do is just mov edx ECX. Okay, so copy ECX. We might use edx for the 3x plus 1 bit. So we'll say something like imul edx 3 inc edx. Okay, so edx is 3x plus 1. And what we might do down here is shift right ECX1. I'll say down here ECX is x over 2. Okay, so if shifting ECX right 1 space ended out with a 1 in the carry flag, then what we know, just because of the way that the shift instruction works, we know that ECX must have had an odd number in it, since we just shifted the 1 out. So what we can do down here, we can say CMOV, CMOV C. So conditionally move on the carry flag being set, ECX EDX. Okay, so if ECX was odd, then replace its value with 3x plus 1. And let's just have a bit of a scroll down. I think that's about all we've got to do. So that means that we can get rid of loop tail. We can get rid of this odd. We can get rid of this. We can get rid of this. All the way up to here. There you go. Would you look at that? Okay. So we're a lot less instructions now. But the other good thing is that we've no longer got that all of that branching. Let's hit a run and see what happens. Fingers crossed. Oh, there you go. So 1.56. We're now about 1.56 times faster than the original code, and we're getting the same value. But there's trouble. So there's more compilers available than just the Microsoft one. And what you'll find is, although all of the compilers, a lot of modern compilers are very competent, you'll find that some compilers are better at optimizing certain code, while other compilers will do, better things with other code. So at the moment we're using the Microsoft compiler, but you might be aware of another little compiler, the mighty Clang. LLVM. Alrighty, this is an incredible compiler. It's freely available, so I'll leave links in the video description. Get yourself Clang. Great stuff. But once it's all set up, you should just be able to select LLVM in your project's properties. There is one other thing you've got to change. It's link time code generation. So something like that. Advanced, maybe? I can never find this. Let's just do a search for LT. Right. Here. Yeah, link time code generation. You've got to turn that off since the Dragon doesn't play with link time code generation. So we'll just, I'll just put that to default. I'll get rid of it completely. Apply. Okay, now, I'll just close the disassembly down. Now, we're racing against Clang. Let's see how Clang optimizes this code. Okay, so Clang just taught us a lesson about optimization. I tell you what, don't mess with the Dragon. We're getting the same computation just here, but Clang is faster than our hand-coded assembly. And you'll often find that this is the case. I mean, compilers aren't bad at assembly programming. They're pretty good. So I'm not saying that the Microsoft compiler will always be slower than Clang or that Clang will always be faster. But in this particular instance, Clang has performed really, really well. So it's a good compiler to have on side. Just test which is dealing with your C++ code better. All right, so the performance ratio here is down to 0.85. So Clang is faster than us by about 15 or 0.15. Okay, so what are we going to do? Well, having a bit of a look at this code and thinking a little bit about the way that the Collatz numbers are dealt with, what we can say is if you've got an even number that can be divided by 2 a few times, say it's divisible by 4, something like 12, for example, that's going to divide by 2 twice. So it's going to go 12, and then it's going to divide by 2 to get to 6, and then it's going to divide by 2 to get to 3. So what we might do is figure out a way to skip some of those divisions by 2. If your number is divisible by, say, 16, then it's going to run 4 loops dividing that by 2. Okay, so the way that we can see how many times, I'll just get rid of this code just here. I'll get rid of this too. The way that we can tell how many times the code would divide by 2 is a bit scan. So we want to see where the first one is, which is BSF, bit scan forwards. ECX and ECX. Okay, so we've got a bit of a problem. The bit scan forwards instruction is going to put the index of the first 1 bit, but we kind of need CL because we're going to want to shift right ECX by CL. What we need to do is figure out where the first 1 is. So say it's at position 2, for example. Then we want to shift our parameter to the right by that amount. But we can't because the only way that you can shift a variable amount is using CL. So what we're going to have to do out here is XCHG. We're going to have to get our parameter out of CL and into some other parameter. I'll just choose EDX. Oops. Okay, so let's say how many times is EDX divisible by 2? shift it right by that amount. Okay, so right there we've just dealt with all of the 2's in a row. What I might do is start our EAX at 0, since the first thing we're going to do is run through this algorithm, so it's at least going to be 1. Okay, so once we've shifted that, we've got to add the number of 2's that we found, or the number of divisions by 2 that we could do to EAX, since that's our count. So we'll add EAX, ECX, add those 2 divisions to our count. We've also got to inc EAX, add 1 extra because we're about to 3x plus 1. Okay, then we might just imul EAX by 3, sorry, EDX, and inc EDX. Okay, so if we come down to the bottom here, we're not actually going to reach 1 anymore. We're going to reach 4. Is that right? Yeah, so the last operation we do is multiply it by 3 and add 1. So we'll no longer hit 1, we'll hit 4 if we were at 1. I hope that makes a bit of sense. So if we start this round up here at 1, then the first thing we'll do is multiply that by 3 and add 1, so we'll be on 4. But that should just about do it, I think. So let's just go a bit of a run and see how we do now up against Clang when we're not performing all of the divisions by 2. Okay, something's gone wrong. What has gone wrong? Well, for one thing, we don't need finished anymore. Yeah, that should just about go, I think. Let's see what's happening here. Well, for one thing, we need SAR. Okay, so we've swapped the parameters around. We're not checking if ECX is 4, we're checking if EDX is 4. I don't know, these bugs. Okay, that was quite silly. Let's see how we go now with whatever we've just done. There we go, so we're done. All right, look at that. We're quicker than Clang. How wonderful for us. 1.34 times faster than Clang, so about a third. Okay, so we could just leave it there, but I do want to point out something else that we could do, which is pretty cool. Something I want to point out too that I've looked at Clang's disassembly at some point in the past. Like, this is not the first time I've programmed this. Clang actually uses something like our second version. Yeah, it uses something like the CMOD version. All right, but if we have a bit of a look just here, add EAX, ECX, and inc EAX. What we're doing just there is adding the 2 values, EAX and ECX, and we're incrementing EAX. But I've got 3 words to say to you. Load effective address. What a marvelous instruction. So check this out. EAX plus ECX plus 1. Bam. We can get rid of both of those. We can do it with a single LEA. I kid you not. All right, that's not all though. Let's have a look at this second little thing down here. imul EDX by 3 and inc EDX. Let's load effective address again. Bam. Nice. So we can swap both of those lines with load effective address. One of the cool things about load effective address is that it doesn't take the same amount of time as a normal imul. Yeah, it's quite quick. And we're doing the additions of EAX and ECX plus the addition of the 1 in a single move. So hopefully it'll be quicker. So this is add the divisions by 2 and plus 1 for the next 3x plus 1. And this one down here is multiply EDX by 3 and add 1. Yeah, so that should be quicker again. Let's just hit a bit of a run and see what we get. I can't remember the other time. But here we are down here. We've got a time of 1.6 times as fast as Clang. So that's pretty good performance, really. I think when you're dealing with code like this, it's not easy to SIMD. It's not easy to vectorize. So you can't really hope for much better performance than that unless you drastically change your algorithm. If we go back to the Microsoft compiler and see how that's going again, because I've kind of forgotten. I think we thrashed it. Yeah, there you go. So we're at about 3 times fast as the Microsoft compiler. So that's a pretty good turnout. Anyway, I just wanted to share that with you all, and I hope that was interesting. Just a bit of a rundown on how I might tackle optimizing some C++ code, and have a bit of a go yourself. See if you can get quicker than I did. I want you to have a beautiful day, mates. Thank you very much for watching my little videos here. Have a good one.